Hello, everyone, and welcome back to the AnyLogic Conference 2021. So far, you've heard a number of great presentations to kick off the conference, and by all means, we will continue. Next up, we'll hear from Patricio Gallardo, a research assistant at the University of Canterbury in New Zealand. Patricio is going to give us a presentation on strategic concept design of freight systems and optimization, a simulation approach for StratCode. Welcome, Patricio.
Hello, everyone. Good afternoon for those in the Pacific region. Good night to everyone else on the other side of the world. My name is Patricio Gallardo. I am a research assistant at the University of Canterbury, and today I am going to share a bit about my work. My area of research looks at transportation as an energy system, and for the past 4 years or so, I have been working on the development of a methodological framework for strategic planning of freight systems. I will address this briefly in the upcoming slides. This is often a cartoon that I use often in my presentations. A picture is worth 1,000 words. So transport is the sector with the highest energy demand, most of which corresponds to oil derivatives. Oil's high energy return on investment, containerization, the expansion of the road network, and the deregulation of trucking have turned the freight sector heavily dependent on fossil fuel resources. And these dependencies represents a wicked problem whose solution requires a radical transformation of the system. This is an extract from an IPCC report on climate change mitigation, which highlights the lack of tools to quantify greenhouse gas reduction and their cost in the transportation sector. My work aimed to address this gap and proposes a set of tools to simulate many transportation infrastructure options and their energy emissions and cost consequences. We performed a case study of the North Island of New Zealand, and a conceptual low-carbon design of the future freight system was generated. There are some limitations in the state-of-the-art of freight modeling methods. Current models reflect the status quo where travel time and cost are prioritized over environmental concerns. Existing models can paint a pretty picture, but they can be based on uncertain economic projections and technological developments. Data on freight movements is scarce, as the information can be commercially sensitive and transport surveys are costly and infrequent. And the lack of a logistics component is often cited as a major limitation in freight transport modeling. This is the main contribution of my work. It is a multi-method framework with different components and objectives that address the aforementioned limitations. It advances freight supply chain analysis to inform low-carbon transition pathways. The arrangement of the framework is novel in the sense that it connects multiple perspectives, network planning, transport, and terminal operations into delivering a long-term conceptual design of the freight system. There are 3 main components: a freight distribution model, a freight network design model, and a discrete event simulation model. So the boxes in blue here in the framework. Data used by the framework is based on official documents and databases and open source geographic data. In brief terms, the framework adapts a simulation component to conventional transport modeling approaches. The integration is achieved through a central GIS-based optimization component. Component 1 can be viewed as a preliminary step that enables to arrange data sources into structures compatible with the subsequent steps. The component combined different methodologies, including iterative proportional fitting, calibration of gravity models, and linear optimization. The final output consisted of a dataset with several different line features representing origin-destination pairs between different facilities, including forests, dairy factories, warehouses, and ports. Some of the locations were obtained through the formulation of iterative queries using a Google API. On the other hand, forest locations were derived from an open source land cover dataset upon the application of several geoprocessing scripts. The next component inherits elements from the field of multimodal transport planning, and ArcGIS was used as an instrument to build a virtual network, meaning that it allowed to systematically detach the operations involved in multimodal transportation and to effectively allocate the corresponding costs or attributes. The component allowed to deliver different layouts or scenarios based on energy and travel time optimization. The process was iterative. The algorithm was implemented for every OD pair delivered from the distribution component. The process involved loading a network dataset, loading the locations of the facilities involved, running a shortest path optimization, which for in ArcGIS, Dijkstra's algorithm is hard-coded onto the software, extracting relevant information and building a database. Optimization was carried out using either time of delivery or energy use as cost attributes. We also assessed other aspects, including the addition of a new railway connection and a full shift in freight activity from ports of Auckland to Northport, which is a port up north of Auckland. The architecture of the algorithm allowed to deliver different outputs: traffic assessment, location of intermodal terminals, and optimal delivery plans. Now we get onto the simulation part. So there are recent freight models that have adopted simulation as a modeling resource. Some of these models inherit structural elements from supply chain analysis, specifically queuing systems. Every stage of the supply chain is modeled as a network of service nodes. Every service node often contains a source block, a queue block, and an activity block. Recent models also use an agent-based approach, which has important advantages, as it can capture the heterogeneity of actors and objects in freight systems. Often these agents are categorized into two groups: cognitive and non-cognitive agents. Moreover, there are communication protocols between agents, often in the form of messages and contracts. Simulation is used to enhance the analytical solution delivered from Component 2. AnyLogic was a good choice of software because it enables users to integrate GIS maps. It provides a multi-method environment. It provides the specific libraries for simulation of railway systems, manufacturing, and warehouse workflows. In the model, agents, which were in my case facilities, terminals, ports, trucks, and trains, interacted with each other in response to shipping orders following a timeout rule. The performance of the system varied with changes in network infrastructure. So we looked at changes at interventions on the tracking, single tracking or double tracking of the railway network, train cruise speeds, and terminal parameters, the number of resources and the size of the rail yards at these terminals. There will be different workflows depending on the facility type. For instance, every factory agent has parameters including the geographic coordinates, identification code, and the hub assigned for a shipment. When a shipment order is sourced, it is assigned a truck agent and moved either to a final destination or to an intermodal hub. Depending on the location of the facility and its accessibility to the railway network, there's 3 services that are considered: truck-only, intermodal, and rail-only services. Shipping plans generally involve intermodal trips based on connections also extracted from a database. So this was the database that we created with the second component. AnyLogic facilitated for the modeling of this process, and the ability to interact with a central database was a key feature. Usually there's an exchange of information between agents and the central database, and data is extracted through query SQL commands. The figure here represents our workflow for a terminal type facility. A train enters a terminal and is assigned a track element from a collection of tracks representing a rail yard. If cargo needs to be unloaded, a crane is seized from a pool of crane resources. Unloading times are simulated through delay blocks. Cargo is unloaded from the train and placed on a storage queue, where it can be picked up by a truck and delivered to its final destination. And once a train unloading is over, the crane resource is released back to the pool and the train is ready to pick up any pending cargo from a second storage queue. Train loading proceeds in a similar manner as before. That is, a crane is seized during train loading. After loading and unloading operations, the train enters an exit queue. In case there is a train that is not required to drop or pick up a load, it directly enters this queue. Auxiliary variables and functions are used to monitor the conditions of trains that enter the rail yard and to manage their movement. Movement between the rail yard and the exit track is also modeled with the cease-release approach. The exit track is established as a resource to ensure that only one train exits at a time. And a hold block is also considered before a train exits, which is activated when trains are approaching the terminal from a direction opposite to that of exiting trains. For some terminal agents, the actual process can be more complex because it may account for the operation of multiple train lines, as we'll see in the next slide. This is a short clip of model execution, which includes a representation of the area of study, the Upper North Island and the railway connecting Moriwa here to Waitakere, north of Auckland. 6 railway services were identified from the traffic assessment delivered by Component 2. There are workflows inside terminals, ports, and origin and destination facilities. And there's also a general workflow, the main agent, where the transport operations are coordinated. AnyLogic offers routing functionality, allowing agents to move through road and railway networks based on data extracted from OpenStreetMap servers. However, our model was based on an upgraded railway network with a direct connection to Northport. Another major advantage of the software was the ability to include customized networks. After a bit of extra work, we were able to connect AnyLogic's default network service with our custom additional link. Component 3 provides the flexibility needed to connect the perspective of network planners, transport, and terminal operators. It provides an holistic view, simultaneously evaluating network and terminal capacity. It delivers a conceptual design for a system that can meet the current freight task with half the current energy demand. A recent official report predicts that future operation of Ports of Auckland will be increasingly constrained in its economic and environmental viability due to landside infrastructure friction. The GIS-based network model was at the core of the framework and was implemented to explore the impact of this move. The analysis is also contemplated the addition of a direct railway connection to Northport. Finally, time and energy use were optimized in different scenarios. The model allowed to evaluate network traffic for different scenarios. The strategic locations of intermodal terminals were obtained upon the traffic assessment. And moreover, model implementation allowed to delineate the railway services needed to meet the freight task given a specific network layout. The traffic assessment also allowed to identify road segments that can potentially be considered for future railway extensions. And there is an evident trade-off between time and energy use. Overall, emissions are proportional to energy demand as expected. And given the case that a full shift to Northport takes place and trucking remains the dominant mode, greenhouse gas emissions can reach up to 250,000 tons of CO2 equivalent. On average, scenarios where energy use was optimized are associated with travel times 170% higher than those of time-based optimization scenarios. And in contrast, scenarios where travel time was optimized have 86% more energy demand than scenarios based on energy use optimization. The best case scenario shows a 47% reduction in gross emissions is possible. I want to highlight a few results from the simulation experiments. 6 simulation experiments were included, and the table summarizes the setup, parameters, and resource utilization for each simulation experiment. The experimental setup allowed to evaluate trade-offs amongst parameters on each test and demonstrate how the model can be used to streamline the arrangement of the conceptual design. The first experiment is based on a predefined number of resources at different terminals and on single track sections throughout the network. During experiment 2, the number of resources is adjusted in order to improve utilization rates while maintaining smooth operations throughout the network. In experiment 3, double tracking is implemented in some sections. In this case, the major benefit of double tracking was the reduction of round-trip travel times. by the way, AnyLogic's visualization tools were useful means to validate our model. Specifically, the generation of train timetables allowed to visualize the feasibility of running daily round-trip train services. We also included visualization for queuing levels at terminals in order to work out an adequate number of resources at these facilities. Comparing experiments 1 and 3, double tracking cuts round-trip times by approximately 500 minutes. In experiment 4, we explored the impact of faster trains. Cruise speeds were increased from 35 kilometers per hour to 50 kilometers per hour, leading to a further 500-minute reduction in round-trip time. The reduction in travel time can be exploited as more trains could be added in case needed. Moreover, these additional time savings can enhance additional clearance for loading and unloading operations at terminals. In experiment 6, we looked at the impact of number of wagons. The addition of five wagons per train slightly increases round-trip times if compared to the timetables from experiment 1. Still, in experiment 6, all trains managed to do a round trip before the end of the day shift, despite low train speeds and single tracks throughout the network. It is worth mentioning that the values reported refer to cruise speeds, as the software allows to model train acceleration and deceleration within terminals, and speeds vary accordingly. It can be seen that by far, experiment 4 is the most costly arrangement, to a large extent due to an upgrade on the network to allow for moving faster trains. Experiments 1 and 2 have relatively low cost, but are not satisfactory in terms of performance, as queue levels within some terminals accumulated over time. We are left with experiments 3, 5, and 6, and experiment 6 can be considered as the most cost-effective pathway, and surprisingly, it proves that substantial reductions in energy demand and greenhouse gas emissions do not necessarily require costly measures. Moreover, the results suggest that the implementation of key intermodal terminals should be a priority. Accessibility to the intermodal network infrastructure is the key. Some conclusions here. I am just summarizing the main outcomes from the implementation of StratCode. It is probably worth considering a few recommendations. More detailed applications of StratCode will likely depend on more robust data sources. A good benchmark is the Commodity Flow Survey from the U.S. Department of Transportation. Coastal shipping can also be considered in future assessments. However, the adoption of an additional transport mode implies higher complexity because it would require the addition of transshipment GIS features, transportation attributes, and shipping networks. This also leads to higher complexity for the simulation component and hence additional computational resources. These are some of my references. If you are interested in the details behind this work, there's a paper that was recently published. The reference is here. So have a look, and my details are also on I think have been uploaded to AnyLogic's platform. So feel free to contact me if you're interested in this kind of work. Thank you very much. Well, the first question, the first question, how's the present global supply chain operating when COVID-19 is still occurring? So I see that there's a huge problem. I was just reading this on an article a couple of days ago. And the problem, one of the big problems, is how to handle the movement of empty containers from one place to another, and that's also a local problem here. So there's some industries that have managed to make their operations more resilient, and that one such industry is the dairy industry. So they have managed to, they used refrigerated containers, or they're called reefers, to export dairy products from New Zealand. So they have managed to balance the incoming commodities without going commodities through the implementation of inland terminals. So that's one way that they have, one strategy that they have used to overcome these disruptions in the supply chain. But with COVID-19, it's something that was unexpected, and there's not a lot of research on this area. You know, this we're going through unprecedented events, and there's probably going to be a lot of research in the future on this particular area. Were all the GIS points available, or did you need to add them to your model? I needed to add them to my model, but this is one of the advantages of AnyLogic. It allows you to import geographic data, whether it is GIS points or I was talking about line features and creating your own network. So all these geographic or features can be imported through to AnyLogic very easily as well. And you can even build your own custom networks. This was a huge advantage as well. Often the way that you bring these elements into AnyLogic is through a shapefile. And there's good tutorials on this. That's another good thing about AnyLogic. There's probably somebody already thought about these things, and there's really good documentation on all these smaller problems. What was the model runtime like with the GIS functionality? Well, I cannot run the model from my laptop, and that was a huge disadvantage. That's why I was not able to share more videos, because I kind of worked on my presentation during lockdown here in New Zealand. So I often run my model from my desktop computer at the office. So yeah, it would depend on the resources that you have, but definitely it will be tricky to running it from a conventional laptop, I would say. So you would need a lot of RAM memory, especially. I mean, depends on the complexity. You know, you can, the simulation, the idea is that we want to get a reasonable representation of your system. You don't want to get into a high level of complexity, as you will be limited by the resources. So there's some trade-offs to assess there. And what do you think it was the most important or challenging part of the modeling process? This is a good question, and this is something that I have failed to include in my presentation. But in my case, I have different terminals located in the GIS space, but not all these terminals they are similar in a sense, but they are also different. They process different commodities. So in a sense, they are similar agents, but they cannot be treated as such. So one key feature of the model is the implementation of Java interfaces. So this kind of allowed me to provide a common protocol to exchange information with different agent types. You can see a lot of the examples or the tutorials. You're generally dealing with similar agents. You know, you communicate with a set of agents, but they're all the same type. But it becomes more complex when you want to interact with different agent types, and this is where Java interfaces were really useful. I don't remember the specs from my desktop computer, but I can, if you can flick me an email, I can share those specific details with you later on. Yes, I did publish this. So if we go back to, that's the reference right there. So it's, the name of the journal is called Energies. It was published, this paper was published in June. And yeah, I think most of this work that I've talked about today is summarized and very, well explained in this paper. Well, thank you guys very much. I hope this was useful. Thank you.